Anyway, that's me. I'm giving this talk, and we'll talk about passions later in this talk. But let's start with a little bit about you. By the end of this talk, I want you to be able to go online and download what we just shipped today. Dynamic Language Runtime Alpha 6. The Redmond team just put it out this morning. I just checked. Download URL will be on the slides later. But back to you. I would expect that many of you are dynamic language users. Just show of hands, how many use routinely dynamic languages in your life, either professional or as a hobby? Awesome. How many of you are compiler geeks? That's the other part of the attendance I'm curious about. Oh yeah. So you might have written a compiler or 2 or 3 or 5, and perhaps you're even contributing to one of the open source popular dynamic languages. So let's look at where they are and what they are. There are many of them, right? Example is obvious. There are many more than on this slide. And just like football, in addition to all these features they have, they inspire passion in us. And one of those passions is a rebellion. So now that we've done that, we can move on and start with the real presentation. So why did we come up with the dynamic language runtime in the first place? Well, there is a lot of languages, many more than the previous slide showed, that are becoming the driving force of the web. Ruby, especially with Ruby on Rails. JavaScript, come on, runs Google, right? So we want to make it easy to develop dynamic languages. With this dynamic language runtime that you can download from the URL below, if you have a notebook, just start typing, because the Alpha 6 is there right now. You can download this thing and start building your own dynamic language. Or, better yet, take your existing dynamic language and port it, or start playing with porting into dynamic language runtime. What do you get is benefits of the .NET platform that this whole thing runs on. The benefits that we see for ourselves, you probably discover many more, are obviously garbage collector, which is one of the best in its class. Second, the .NET platform the runtime runs on has just-in-time compilation and ahead-of-time compilation, JIT and NGen. It comes with very rich libraries. It's pretty awesome. You write a little sample language, and voila, you have all these libraries to do whatever you want at your fingertips. And we'll see that in the next slide, essentially. And tools, last but not least, definitely not least. The tools give you immediate debugging support. You can plug into profilers, though that story is not quite polished. But debugging is great, as you'll see right now. So let's take a little baby steps, nothing big. What I came to show you are 2 languages. This is the first one of them. We just hacked it up over the weeks as we need to test some features of the dynamic language runtime. It's called ToyScript. Obviously, from the name, it's clear that nobody can use it for any serious application, but it's great for showing you how the runtime works, and we'll be hacking on it throughout this whole session. So this is ToyScript, kind of like C#, a little bit of Python in it, you know, dynamic language. There is many varieties and many in between them. As you read and absorb this code, notice one important thing. There is no single addition in it. We'll get to that later. But otherwise, you know, it prints something, does some calculations, and calls a function sub with 2 things. And about the line 15, things get really interesting. Notice what I did when I wrote this little thing, or when my team wrote it. was very little work in terms of .NET interop. It comes for free with targeting the dynamic language runtime. So as of line 14, 15, I can start importing system, and I can do system.whatever, and the whole library is there for my use. And then when we move on, we can print date time now. We can see what date it is and calculate factorial also without addition. And do some more tricks with math library, create a hash table and store something in it and retrieve it. Quite simple. So let's run it and see what happens. Now we hit a breakpoint, right? As expected, or maybe as not expected, because debugging stories in many dynamic languages are not the most polished overall. With dynamic language runtime, it comes fairly cheaply. And as we step through the code, it does what we would expect. That will print X, which is going to be 4, and so on and so on. Calling the function, printing the result. And now we're talking to the .NET framework libraries. So my current directory is TechEd, if you're interested, and it's 10:53:49. So we got plenty of time. Now with the loop, you see that the positioning in the debugger is not quite there, but I have another language later that's much better already. So we'll see how things can work even better. Let's keep running to print the factorial, which should be 120 as expected. Now this is interesting. What I've done, system.math.sign on the next line is a method. And what I can just pull it out and have a first-class method, if you will, even though .NET doesn't natively support these things, is the runtime that does. The dynamic languages runtime. So I just pulled it out, and we can see that this sign thing is what we call a method group. Unfortunately, it's not very readable. Let's do this. So I can even expect the locals. It's a method group which represents the sign function as a first-class object. Now I can call it. In C#, you would have to do math.sign, whatever. Now we can just pull it out and call it directly. And to close off, we can just new up a hash table, put something in it, and this will start script talking. Now back to the talk. So if I was writing a traditional compiler, the front end, which we pass ToyScript source code, a function that adds 2 to anything we give it, we would have to tokenize it into a stream of tokens. Then after that, we parser unleashed on the thing, and we would end up with an abstract syntax tree, which would look something like that. We just bother with a return statement, not the whole function. The space is limited. Return add of constant plus some named expression that we'll have to resolve in the later compiler phases. In the traditional backend, I would then take this AST, do a bunch of analyses on it, and start emitting IL. Now the IL could look something like that. We would load a constant, load the other arg, and call a little helper that does the addition. Now notice that in dynamic language, it's not obvious from the source code what needs to happen. From the source code over there, we knew that 2 was a constant 2, and if we're lucky, we know that it's an integer and not double. Perhaps we should be lucky because the language should define that, but we don't know anything about the A. So for that helper, perhaps we should just pick that it's object, and the helper will then introspect the objects, talk to them, and figure out what it means to do the addition on them. So we just cast the 2 to object to just have one helper that deals with that all and call that. So obviously we have to write the helper. So it's going to be stashed away in some runtime library, And this could be our compiler. Emits IL and has some runtime library that comes with it. This is the library that defines the language semantics, which goes and introspects things and figures out what it means to add two things, for example. And of course, the front ends, the parser, the tokenizer, the language analysis that defines the semantics. The actual code generation is just a tedious task. I mean, if you've done it, it's kind of easy for binary expression and stuff, but if you tried exception handling, generators and such, it becomes kind of hard. So we've done it. With the DLR backend, we also start with a AST of your language. But instead of IL, which is the tedious job nobody wants to do, you just create something what we call DLR tree. It is a tree similar to your abstract syntax tree, but it's got some additional features, say. It's fully bound, so there is no such thing as saying this is just a named variable or named expression. You will have a variable, and the expression is going to be bound to it. Just like the bottom right side of the slide, we have expression that is bound to variable. So your language analysis will figure out what needs to go where and generates this AST, saving the horrible tedious task of IL generation. So in this case, you just generate statement return, and the expression it returns is a call into some helper that we've already written, which is part of the language semantics. So really, nobody can do that for you. So you still have to write it. But instead of doing the IL, you just do something way simpler. We brought the language of languages, if you will, from IL up one level to trees, which are way easier to deal with. So now I think this is quite obvious, no news here anymore, because what we give you is opportunity to focus on your language, do the tokenizer, do the parser, do the analysis, create the ASTs, and we'll do the code gen. There are other features in the DLR, which we'll cover a little later, but just as the preview, the DLR can learn about the semantics of your language as you run it. And this learning is cached in what we call dynamic sites, and the support for that are also in the DLR. So it's what on the slide reads extension, the dynamic operations, the support for dynamic operations, and the learning that comes with that. The language learns about your dynamic language as it runs. So the DLR trees are the language that DLR talks. If you've seen LINQ, how many of you have seen LINQ in any form or shape? Well, everybody. So I guess the rest of the talk is going to be very easy for you, because the trees we have in DLR are just like LINQ trees, except we need to run real languages, not just expressions. LINQ trees just express expressions. Well, it's not enough for us. We need statements. We need the dynamic support. That's what we added. The expression side of the trees still look very much like LINQ. We even try to match the names. Now, of course, I'm going to get a question, why aren't they the same thing? Well, we hope that one day they will be. We're just not there yet. At least I hope. So as for the statements, we've got the return that we already saw. We've got if statements, switch, throw, try, whatever you would expect. Now that one action expression that is spelled out at the bottom is the dynamic one. It's the only dynamic one. And essentially it says, I don't really know what happens at compile time here. All I know is that this kind of action takes place. But do I know whether it means that I'm adding two integers or whether I'm adding two Python objects which define under add on them? No. I don't know that. I'll have to figure out at the runtime. That's why I do this action expression thingy, which at runtime will ask the language, so what do I do at this particular situation with these two arguments that came in? Give me the answer. We'll move from there. DLR will learn, and the machine keeps running. To create the ASTs or trees, I might use the term interchangeably when referring to the DLR trees. We have factory methods just like C# in LINQ. The LINQ calls them expression dot whatever. We call them AST dot whatever, just to distinguish them a little bit, because They're really very much alike. And here's what the whole function would look like in the format of tree. So we have that helper that we need to provide. We have that add to whatever function. And we're generating, this is the full version of the DLR tree for it. As for functions, DLR expresses them in the way of code blocks. Perhaps not the best name, but we use it also for class bodies, so just calling it function is not quite right. We'll get the names better though. So that code block has one argument, a parameter called a object, just like the source code does. And the body is a return statement calling to the helper, take the 2, convert it to object, and the right side is bound expression to the parameter. And that's what the language analysis did. It figured out somehow that the a in the body, it's your language doing this analysis, that the a in the body is actually the parameter. So all it does is tell the DLR that this bound expression is bound to the parameter. It's a variable just like any other. So expressing that is very easy. And this is how you would do it in the code. First line, just create a code block and give it a name. Then you would add parameter to the code block, give it a type. And as the last thing, you would build the return body. And because building trees is really nice thing to do with these nested calls, you will see many of those today. But it's just cool. You're essentially building the tree as if you were writing the code. Now imagine if you're using LINQ. You write LINQ, so you write C#, and the C# compiler underneath generates the tree structures, the expressions, the nodes, if you will. Now, if one day, and I hope, we get to the place that C# LINQ expressions will be as rich as these trees, wouldn't it be cool that we could just write that code in C# and not with ast.return, whatever? We would just write return toyhelpers.add, pass 2 things, and cast the whole thing into DLR tree, and then be it. We're not there today. I hope that one day we will be. I don't know. Can't promise anything. So now that we know how to do this, let's do some hacking. That was his first demo. And if you look at this thing, it's full of additions. The reason there was no addition on the first slide was that it's broken in the compiler. I broke it intentionally so that we can fix it. So if I run this thing, I'm going to get an assert. This is not implemented, obviously. I expected that. So let's do a retry. Let's look what happened. So looking at the call stack, here's where we are. We are in the toy script AST as it came out of the parser. And we're generating the DLR tree. So the AST in the parser, let me just bubble up from the assert. Here we go. So the AST from the parser has left side, which happens to be constant with, this is the span of it, with 2.0 value. The right side is named A, just like you would expect. We're looking at the body of the function add2. So this is the expression we have there in the debugger. Left side is 2, right side is A. So it's not implemented. And based on what you just saw, I think you can just tell me what to write to get it working. So in the language of the DLR, let me just kill this so I can type. Comment this out. We need to do ast.call. We're calling the helper, right? Then the helper is somewhere in the toy helpers, and it's called add. That's that. There is only one, so I didn't need to disambiguate with signature. And then the two things, what do I pass to it? First one is left, generate recursively. And the right one is right, generate also recursively. And that should be it, with one minor caveat. What if the constant expression that's hanging in there right now, actually the 2.0, is not an object, which it is not? How am I going to call this function? We have to do some conversions here because just like link trees, the DLR trees require strong typing. It's kind of strange thinking about it that dynamic trees require strong typing. You can think about it as the whole DLR trees minus the action expression are well defined, have very good semantics, and one way to achieve it is just have static strong typing in the whole system. So if I do 1 plus 2, it's as if in C# you did 1 plus 2. It's when I want to get into the dynamic world, I use the dynamic action expression and things get wild. So this side of things is fairly simple. We're taking something that can be not an object and we just need to cast it. So for that we have a little helper, AST convert helper right to object, and same thing for the left guy. Oh. Yeah.
The toy generator, that's what's walking the AST?
Yeah, toy generator is a very good question, Michael. So the toy generator is a storage for a few things, if you will. As I'm walking the AST, I need storage to take notes. One of the notes is, for example, which variables I already declared, so I can look them up. It's stored in the toy scope up there, line 23. Otherwise, just a bunch of utility stuff and the way to create the code block. So as I enter a new toy function, I create one of these, which will create the new scope and create a code block, the thing that we call add2, the unfortunate name code block, and start remembering on this toy scope all the variables that we already have, a dictionary of them, parent, stuff you would expect. And this machine is walking the AST, generating on the other side the DLR trees. Good question, thank you. Okay, where we were, binary. And of course, we just need to return that thing, and it should be ready to go. So what we did, yes? Is the question, is there any difference between convert and convert helper, or convert? Yes. Very good question. Is there any difference between calling convert and calling AST convert? Convert will actually do the work, right? You give it number 2, and you say convert to double, and outcomes 2.0. This AST convert means create an AST node that represents conversion or cast, if you will. So at compile time, it will emit instruction cast to object, or box in this case. So we're just building instructions for the back end to emit the code correctly. Good question, thank you. So now I hope it should work. So we're calling this toy helpers add. Let's look at what the helper says. Here it is. It's also not implemented. Let's put breakpoint in here and run the thing. So this time we should compile just fine. You see we came in here. And on the call stack, we are in the add2. So somebody, DLR, did code gen and called this little helper. Now, of course, what does it mean to add 2 things? Let's see what they are first and just keep hacking. Okay. Oh. Introduce the backslash there. Intentionally. There we go. So we have A, we've got B. How did my debugger get messed up? But at least let's restart this thing and stop here again. There we go. So they're both doubles. So now we can implement, if you will, addition for doubles. Kind of poor man's version of the whole thing, which would be, dealing with strings and what have you. So let's see. We can write something as if A is double and B is double, return double A plus double B. Fair enough. Otherwise, it's going to blow up. But, we're dealing with doubles, so whatever. So I actually calculated a lot of things. As you see now, in the original source, we're in the other function that's adding two things, not just two to whatever. And in fact, if we look at the caller, walking the call stack even higher, we're adding two strings. We're calling with hello Barcelona. So we have not implemented strings, right, in our toy helpers. That's why we hit this assert again. So let's add strings to it. If A is string and B is string, return string A plus string B. And I could go on and on and on, adding all the types and all the combinations. You kind of see where this is going. We can run it again. This time, it will have added the strings and printed hello Barcelona. And it says, all done. Decimal is not going to work, and it shouldn't. Why should decimal not work? We're passing decimals into this function from here. We pass decimal to A and B. See, object decimal. Do we expect decimals to work? No. Why? Exactly. They are not strings and doubles. So we would have to keep expanding that list for every type that exists and for all the future types. It's kind of not what we want to spend our days doing, right? So I'll leave it at that. Decimal doesn't work. In the next demo, we'll get it working, and I'll show you how. So let me just clean this up. And back to our little hacking cats. So this is what we did for addition. When we saw addition in our AST, we said, I don't know how to do it at compile time. It's just too complicated. Let's call a helper, method call, node, which calls toy helpers add and passes two things to it. Both are bound to whatever the respective expressions are, or constant in the A+2 case. Now, what does it really mean? We've already seen that it's not as easy to add two things as it might appear. If I write in a C# 1 plus 2, we had strings, we had decimals that we didn't succeed getting to work. We have other things that are addable, which we might want to add. So things can get kind of complicated. And what's even worse, we could estimate how to do things. We could write a huge helper that lists them all and some crazy cases we can think about. But what would happen is, what if I then passed you the one that's at the bottom of the list? We'll be checking forever to add two things. And if integer happens to be at the bottom of that list, we've tested for double and byte and string and everything, and integers at the bottom. It can be silly to do that. But if I did that, integer addition will be slow. What if my program only ran on integers? It'd be just slow for no reason. So what we can do is use the DLR feature to help us with that. And find a better answer to what A plus B is, not a call into helper. Not much has changed in this picture since the last one that looked just like that 2 slides ago. At the root was a method call and then 2 bound expressions. Now there's action add, and the rest is the same. We just replace the root and magic starts happening. What we're telling the DLR at this point by creating the tree that looks like that is we don't know what to do at compile time. Before we were quite sure, we wanted to call that helper. But now we're not quite sure. Somebody needs to ask some questions at runtime what needs to happen. So by giving this to the DLR, we're saying we don't know yet, we just know it's addition that's happening. Addition of whatever things are coming. What the DLR does, it creates this, we call it dynamic site. It's stashed away somewhere statically, you never see it. And in the place of the source code of the IO stream, if you will, where the addition or the operation should occur, it just calls invoke the thing. Very simple, one call instruction, call into the dynamic site to do whatever. And the first thing that the invoke does, and the only thing that it does, it blindly calls the delegate that's stored within it. It's the delegate that's interesting, and it's the delegate that changes. Everything what you see now is constant. Since DLR compiles the tree, it doesn't change. It's the delegate that is interesting. When it's initialized, it's quite simple. It starts crying for help. I don't know what to do with these 2 things, like integer and byte. How do you add them? I have no idea. So your language receives the question, what do I do? Runtime is asking, what do I do with these 2 things? And the answer is going to come back in some form. We'll talk about that soon. And we might insert, and the delegate is going to morph into something that can add now integers. We had 2 integers coming in. The delegate cried for help. I don't know. And the answer came, and now we can update the delegate with the way to add integers. And this is how the DLR is learning. Now, you didn't do anything to keep this machine running. The DLR did. So now it can add integers. And so long as I have integers, WAL keeps running fast because this is the only test. So what we saw is A plus B calls into the site, calls into the delegate, boom, answer comes out. The first time something else shows up, what happens? Say we have integer and double coming, or 2 doubles. What happens? We cry for help, right? So somebody is going to ask somebody else for help. We'll see how that happens on the next, or maybe the slide after that. And the answer is going to come. If they happen to be doubles, then add them as doubles and off you go. So long as my program is running on doubles and integers, it's screaming fast. It doesn't have to do a zillion other checks for strings and whatever. As soon as I see one, I'll figure out how to deal with them. Now, there's a lot of magic that can happen here. The magic could be, what if I haven't seen integer for a while? Can I just remove it? Yeah, why not? We can introduce some way that the helper can monitor itself and throw away things that we haven't seen in a while. Rearrange them based on how often they are used. All that is possible. I'm not doing it yet, but we already are doing some optimizations. For example, I'm lying to you right now because if you see integer and after that you see double, we will not add double. We'll replace it with integer. And only if you switch back to integer, we'll place them both. So if your program is running on integers happily forever after, and then switches to doubles and runs happily ever after again, and never brings integer again, there's no need to look for integers. So we already have that machinery in place. However, when you come back to integers, things will look like this. It is this one test that is interesting. It is the answer to the question, how do you do the operation on these things that I just happen to receive? And we call it the rule. Rule has 2 parts. the condition in the if, we call it a test, and the actual work, which we call the target. Who makes the rules? They describe the semantics of your language, right? So it's the language that does. And there are some rules you don't want to care about. For example, how do I call hash table add with with a key and a value? From a system that is built on .NET, you would expect that that would just happen, that I wouldn't have to worry about it. So there are some default behaviors that the DLR implements. But the first question goes to you. How do you do this? So you have the first right of refusal. You can say, I'm adding strings in such a way that I always add hello to the end of them. Okay, fine, obscure choice, but valid. If the semantics of the language calls for it, you can do that. If not, you can just call DLR by saying, I don't know. So the communication, to repeat, happens if that help me helper is called. The DLR, the runtime, will address the language and say, tell me how to do this thing. I'm holding two things here. I don't know what to do with them. This is the operation. These are these two things. Tell me what to do. It is not do it. That would not lead to learning. It is tell me how that is important. And then the language can answer via what we call an action binder, producing the response. Or it can just say, I don't know, in which case the default behaviors kick in. Now, what does the answer look like? What do you think? Is it IL? Is it, yeah. Delegate? Almost. Is the trees. So the language just generates the trees describing the answer or how to get it. And off we go. So you see, you can even think about the dynamic language runtime as this machine that is a bunch of, like a cherry tree, if you will. It's a big machine that's running a bunch of little different trees, some smaller, some bigger, some are whole programs, some are these little snippets, but it's a machine that's running trees. And has a bunch of caches that remember the trees that it's already seen, throws away the ones that are not used anymore, garbage collector is sweeping away, and things work nicely. So it's a tree processing machine, if you will. So, for example, if we're adding a string, the test would look something like that. We would build an expression that tests argument 1 for string, the argument 2 for string. Now we're formulating the answer to the question that the runtime is asking. How do I add strings? How do I do that? So the language is responding, well, if the first guy is a string and the other guy is a string, that's the test of it. We'll get to the target later, how to actually do it. So the part of the test which says, if the first guy is a string, it's pretty easy. Type is expression, left thing is the argument value, the right one is the type that I'm interested in checking. Same for the other guy, oddly enough. And create binary and, logical and in between them. That's it. So we pass this tree up as part of the answer. This is the test you need to perform in order to perform the action to add two strings. And this is how you would add two strings. Actually, if you add two strings in C#, you will see that C# will generate not operator call. String doesn't have operator addition operator on it. It only has concat functions, so it's just decision of the C# designers to simply, if string plus string means call to concat with two strings in it. And that's exactly what we'll do. We'll call string concat, take the first thing which is coming in, and it's most of the time object, so we need to do the casting, and take the other thing that's coming in, and we know it's a string because the test guarantees that. We just make a cast and pass it into the string concat. And we did that, didn't we? We just didn't do the casting of strings, and the function wasn't called string concat, it was called toy helpers add. It's the same thing. We're calling something well known. So we take the first guy, argument 0, cast it to string. Do the same with the second guy, and then method call string concat with those two things. It's not much different than the front end work we did already. So you see, it's the same trees that work both at, if you will, compile time or AST generation time, and then at runtime when the runtime is interrogating the language, saying, how do you do this thing on these two objects? How do you negate a number? How do you call this function with these 50 things and 3 dictionaries and all this stuff? All these questions are bouncing back and forth, and there is a lot of them. One answer looks just like that. If first one is string and the second one is string, call string concat, cats whatever you have to strings, and off you go. Now we'll take the big leap of faith. We'll actually implement this thing. This is demo 3. The source code hasn't changed much from the demo 2. It's full of additions, also adds 2 to whatever has the generic add 2 things that you pass to it. So before we actually run this, if we did run it, it would behave just like it did before. In fact, why don't we? It's going to blow up on decimals. So we did Hello Barcelona twice, right? And now where we are, in the source code, we're adding these 2 decimals. Right before that, I called create me a decimal with a value 10 and new me up another with value 20 and call add with those 2. So there are decimals coming in, which we can confirm in our helper. The object decimal. Decimal is the type. We haven't implemented it, blows up the same way. Now, we can avoid all this mess altogether simply by not generating the call expression to call into this helper for addition, but dive down into the depth of DLR. So we need to go back to our front end. The binary expression where we implemented the method to generate the AST for the DLR to compile. So it's still the toy helper that we put in. So how do we do the real thing? In fact, I'm going to simply reuse much of this and simply say return AST action and its operator action with addition. I have to say the result. It's for optimization purposes where you can actually, if the compiler has static analysis good enough that if this is int and the other one is int, I can say that my value as an action expression is also int, and things can start propagating from there for optimal, tighter ASTs. For now, I'll just say type of object. And now the 2 arguments, which we conveniently have already in place. It's the left guy, the right guy, right? Just get rid of that. So instead of instructing DLR to call helper toy helpers.add, we're saying we don't know what happens at compile time. We don't know, but at runtime, ask us, and we'll tell you. That's the contract by creating the action expression. So what happens when we actually run this thing and give it to the DLR? Because as you might expect, somebody's going to ask us. And we don't know yet. We haven't implemented it. So let's see what it is where the question came in. Now, what is surprising, essentially, this whole machine, once we switched it over, we have not been answering any questions because we haven't written any code to answer any questions. The toy script language just said, I don't know to all the questions we received, to all of them. For some of them, as I said, DLR will pick some default behavior. For example, if I'm adding two integers, it added them. Now, I still had the right to choose and add differently if I wanted to. It just didn't do it, so the DLR did something that sort of made sense. It's the strings that don't work, obviously, now. Actually, it turns out it's a bug in DLR, and it's because strings don't have operator plus on them, and that's what the DLR looks for by default. So we're exploiting a bug in DLR right now. It won't add strings, so we have to implement it ourselves. However, the decimal is broken, remember, in the helper case? Decimal is now fixed because DLR knows how to add decimals. So that's why I didn't bother to fix it before, yes.
So the default behavior, what language does that correspond to?
You can think about it as the C# behavior. And we still might have bugs in the place where we're slightly different than C#, but the goal is for that to be the behavior you would expect from C# source code, or C# compiled code, whatever. Good question, thank you.
Martin,
Yeah.
It uses the default behavior, but then cache that the next time we come across it.
Yes, yeah,
Yes.
yeah. The question was, if the DLR picks the default behavior, is it going to be cached just the same way as if I gave the answer? And the answer is yes. So we won't recalculate the whole, each and every time we see two integers. It's just we saw two integers. DLR asked ToyScript, hey, how do you do this thing? ToyScript said, I don't know. So the DLR went into its own machinery, produced an answer as if it was me, or ToyScript, and remembers it just like any other, and keeps running. It's when we saw the strings, yes, I'll get to you. So when we saw the strings, DLR asked ToyScript, ToyScript said, I don't know. DLR tried to look inside and blew up because of the bug that we're now exploiting. That's where the things stop, and we have to implement addition of strings. Yes?
Do you have control over the cache and say you want to
Yes, good question. So what if the rules change? What if the rules of the game change? What if my addition all of a sudden starts meaning something else? How do I tell the machinery that things have changed? Does it sort of, yeah. So you have the power over generating the tests. So you can think about, say in Python, it's quite normal that you take a type and you add a method onto it, which will change the behavior of what addition does. All of a sudden, you're not doing something, but you're calling some other method. So for that, you modify the test. You produce little more complicated tests rather than just, is this an integer, is that an integer? We just say, is this integer version 1, which knows how to add by calling this function? And then the test would fail. You would come into the branch, help me, and you would get a chance to look at the object again and realize, oh, the object has changed. It doesn't know how to add itself this way anymore. That rule is invalid, but you can generate a new one which will adopt to the new behavior. So as you swap things, as the runtime and the language morphs dynamically, many rules will just fall off the end because they're invalidated by the behaviors of the language. And it's just all thanks to the test. So yeah, sometimes it might be tricky to write the test to get the behavior right, but it is definitely possible. Yeah. If you download the distribution of DLR and IronPython, you can check out what test the Python generates. Sometimes they're tricky. They deal with versions, and the version updates each time change happens. But we run Python with correct semantics using this. This is what runs Python, IronPython anyway. Thank you, good question. So we've done this thing, and now we've received the question. Toy helper received a question which is expressed as this action. Okay, let's bubble up back to the not implemented. Okay, so the question is, I need to make an operation add on these two things, and I don't have the right answer. So these two things are the args that came in from the runtime. They are hello Barcelona. And if we walk up the call stack a little bit, this is the operator plus. This is where we put the action expression in the tree. This is then what the DLR calls into the dynamic side, which blindly calls the delegate that is now calling for help. We're at the bottom of the delegate. We've fallen off the end, and somebody's crying for help. And we just heard the cry now. So these two frames are where the DLR switches over to the language and asks, how do you do this? Again, how, not do it, so that we can learn from it. So here it is. We arrived into the language, into the toy script, with question, do operation add for me, please, or tell me how to do the operation add for me, please, with the two objects, hello and Barcelona. I've got things kind of prepared in here, but this whole thing is missing. So we've examined, so all the questions come through this place, all of them. And there are many. How do you do add? How do you do negative? How do you do minus? How do you call? How do you invoke square brackets for indexing? I just named perhaps 5 out of 100 maybe that are the dynamic instructions, if you will, of the runtime. So there needs to be some dispatching to route things to the right place, and this is the place. So what we did, line 45, if it's do operation, and if it's add at line 47, yep, just call and make me rule for addition of whatever the arguments are. And that's where we got the assert. So let's go back to the current stack frame. And we were so far happy with the way the addition worked. It added in doubles just fine because it was DLR default behavior. It was just the string that didn't work because DLR has a bug. So we'll just fix it right here. So we're looking at the arguments. They all came through that argument array. And we can now examine them. And we did. Is the first one, arg0, it's line 32. Is it a string? Is the other guy a string? Yep. So this is now when we're talking. We'll give the answer to how to add strings. And we need to give it in 2 forms. We have to produce the rule, which is the 2 things, the test and the target, the actual work. So for that, we do rule set test. And how was it again? Logical AND of is the first one string and the other one string, correct? So we have AST and also now the 2 things, rule parameters 0 is an expression that will bind at runtime to the arguments that are coming in through the function. So this is just a simple way for the DLR to let us reference the parameters to the expression or to the operation. So argument 0 and AST type is the type of the first argument type of string, and also is the type of the parameters second argument type of string. If that is true, then our test triggers and our code will run. Our target will run. And the target will be what again? So now we know that they're both strings, and the target will happen when they're both strings. So we need to cast them to strings and then call, anyone? String concat? Yeah. So rule set target and make return of, and we have to pass the binder for help with necessary conversions if there are any. And this is the actual expression. So it is ast.call, right? Type of string method concat. And now we actually need, because there is like 7 of them or something, we need to say which one we mean. New type array, one that takes 2 strings. Should be it. So that's the method we're calling. And now the arguments we pass it. Anyone? Suggestions? We've already looked at the parameters. Rule parameter 0 is the actual value that the runtime passed us. So that's the very one we examined in the test. That's the very one we'll pass down to the helper, to the string concat, correct? So we would take rule parameters 0 and rule parameters 1. Okay. Just so used to my own way of writing these ASDs that I need the spaces. What's wrong with this code? Needs to do the conversion. Thank you, whoever said that. That's right. ASD convert helper, take this and make it a string. Is this going to succeed? Yes, no? I'm sorry? They arrive from the outside, from the call, if you will. I'm sorry? I'm building the rule as a I'm sorry, can you say it again? Oh, yes. Well, yeah, that won't work. Yes. There's other thing that's not going to work, and it's the conversion. Thank you. Well, yeah. I'm sure we would find out at runtime, and I'd be like, oh, God, what happened? New standard rule. Boom, boom. So what else is not going to work? One answer was the conversion, so I'm adding them both. Now, my question was, is this conversion going to succeed? Or is it cast? Is it? Yeah, why do you think? Because we have the test. The test is around this code, so we know it's a string, string, bam, call. We can do casts blindly. Yes, awesome. Convert helper, type of string. Okay. And now we need to return that rule as the response. So let's look at the whole thing. What we're saying here is make the rule for addition, and we just casually say all we care about is strings. If they happen to be strings, I'll tell you what to do. And I'll tell you the following. If the left one is a string and the right one is a string, then call string concat on both of them. And we can run this thing. Second converter in make return. Yeah. Oh, yes. Yes. Now it should compile and run. So I'll put a breakpoint in here before we run it, and we can check out the rule itself. There we go. And as you use the DLR with your language, we have the built-in tracing for these rules and branches of AST. So we'll just look at that really quick. It looks kind of like C#, but not quite. But this is the code we generated. If the arg1 is string and the other one is string, then call concat and return the result. That comma in there is just because we need the conversion step that was added on our behalf. That's that. That's the.
To make a compiler or translate the other direction, because it seems quite tedious to write this expression.
So as why didn't I make the compiler that takes in that code that I just showed you, this thing, and produces the ASTs? I'm hoping that that compiler is going to be C# one day. And that C# will take, that this code will not be the pseudocode, whatever. I personally hope that one day this might be C#. It's not there yet. It might take, I don't know. I can't make any guesses, even promises nothing, but writing a compiler for that would definitely be nice. And if C# was the one, now that they have LINQ, it would be so cool. So this is the rule that we built. And now we're giving it back to the runtime, and the addition of strings succeeded. And also the doubles, decimals, sorry, at the bottom, is because DLR kicked in and did the work. So that's the magic. Instead of calling a helper, we said, let's call this magical thing where we need to help at runtime, but the DLR asks questions, we respond, and everything happens with the trees. So now we can go back to the talk. I'll actually skip this and move to right to the next demo. There are ways to cheat the runtime into believing that there are methods on things that are not there. Something like C# extension methods. It's quite simple. When I want to show you something really cool, I told you that I would show you two languages. This was the first one. The second one is the real thing. Demo 4. Anybody recognizes this? Yeah. Okay, it's called lolcode. It's inspired by this website, lolcats. I'll just show you the lolcode homepage. Now I guess you're getting why I had so many cats throughout the talk. When I was talking to my friend about what language I should show you, and then I was thinking about this ToyScript thing, he said, nobody's gonna recognize ToyScript. Until today, nobody could even download it. If you download the distribution of Alpha 6, you will have ToyScript in there, which is why I kept it in the talk. But people have heard about lolcode. It's inspired by cats and broken internet chat sessions. That's what it looks like. Hi, Kate, things by. So he challenged me, can you write lolcode compiler? And turns out in TechEd Australia in August, somebody had written lolcode compiler targeting .NET. What they didn't do is target DLR. I did. We have it right here, and it works. So let's go back to the code. You can kind of scan through it and guess what it does. This beginning is declare a variable, import library standard IO, print, declare a variable called code, printed, declare a number, assign, printed, that by 2 times, and calculate the Fibonacci numbers up to whatever you say. Gimme number is input, gimme fib, and then I'm in your is a loop, and ends with K thanks. But because the DLR language, check this out. Ken has system, and it works for free. I didn't do anything. It doesn't add strings, by the way, because I'd have to do the same trick in this compiler. I don't think I did that. So it doesn't add strings, but otherwise it's the full power of DLR. So I can do visible current directory on environment on system. You see that it's reversed, just because this whole language is about unreadability, rebellion, maybe. So unfortunately, its syntax is rather unfinished and not strong enough to support everything. So it doesn't have function call. They keep talking about objects and exception handling, and they have 4 definitions of it. Each one is different. For the last one, they actually changed binary operators from infix to prefix. So what I have here is A up B would actually in the new version read up A and B. So kind of schemish almost style. But this .NET stuff is really cool, and for that, of course, they didn't have, because they don't have objects, they don't have any syntax to call anything because they don't have functions, and they don't have ways to create things because they don't have objects. So I had to come up with some syntax. So this new hash table on collections on system is all my creation, contribution to, if you will, LolCode community. And you know, the rest is, as you would expect, calling some functions and adding things to hash table and bring them out. We can run this thing, of course. Hi world, crazy. Fibonacci, let's do 20 of them printed, and we can step through some things. Debugging works. Let's see. This call add on something with is parameter passing with whatever. After that are parameters. It's also my creation because they don't have calls yet. Same with the concat. See, I couldn't do a plus b or string 1 up string 2. I had to do call into concat because string concatenation is broken in DLR. But we can print it, and it says LolCode rules, as we all know. So at this point, you might think, yeah, this is cool and all, but this is yet another layer. What if I had a little console that I could type these things into? So I wrote it, right? Now it says Python, so I can do def f a b, return a plus b, and call f1 2. Oh, I need to say print 3. As expected. Now, LolCode. Hi. Call f with 1 and 2. Okay, thanks. Bye. Oh, damn, I forgot the visible. Three. What happened? Thank you. Anybody notice we wrote a function in Python and called it from LolCode. LolCode never heard of Python. Maybe they did, but at least this one didn't. It's the DLR that does the magic. I wrote one language, or the whole team of 20 wrote the language of Python, Iron Python, on top of DLR. I spent 10 hours on Thursday and 4 hours in Frankfurt on the way to Barcelona via Copenhagen. Notice Frankfurt via Copenhagen. 4 hours on the stuck at the airport, and this is it. This is a compiler that works. 14 hours of work with debugging, with the communication between the two, and it would be no demo if I couldn't do toy script. It's kind of C#ish, so now I'm like language challenged. But I can certainly call 1 and 2 and do print. It also says 3, and I can just, let's define a little function, toy. And we fixed the string concatenation, right? So, so we can do, I'm typing Python instead, hello plus whatever you passed here. Okay, now let's go back to LolCode, or Python for that matter, toy, Python, print, hello Python, okay. Now we can go back to LolCode, and now my knees start shaking. Hi, pull, toy, with, oh, visible, yes, thank you. See, you're getting better than me. Cold toy with null code. Okay, thanks, bye. Oh, cold toy with, oh, it did work. Yeah, okay, so it was just internal assert somewhere in the compiler, but it did work. So, yeah, it's still kind of fresh, not fully baked, but I figured this is the real demo of the day. Now, we still have a few minutes left. If you have any energy, we'll skip through all this for questions. Or you're totally toast. Yeah.
Any tools for parsing?
I'm sorry?
Tools for parsing?
Yes. How did I build null code?
How to parse it?
What tools? Yeah. Good question. So let me just switch back to walk you through it. We can kill this. Lol code is right here. The parser is regular Bison style grammar. It is a garden point parser generator that folks in Australia put out. It's I believe it's BSD style open source project. You can download it, just garden point, yeah, GPPG it's called. Garden point parser generator.
So can you use whatever parser you want, so long as you generate the DLR trees?
Yeah. The question is, so you can use whatever means of parsing is, and so long as you generate the DLR trees, things will work. Yes, that's the intent. We think that if you have working front end of the compiler and just generate the DLR trees, you will literally have parts of your language running within a matter of days. And you know, beware, when I wrote the lol code, it was just the day before that my friend told me, hey, why don't you do this? And I had no idea about lol code. I had no idea about the syntax. I had to go back and reverse engineer samples to extract the grammar. I had no idea how to use the GPPG and the flex tool that they also put out. They give you both of them. They both generate scanner and parser in C# that you can just put in here. So here's the parser as it comes out of the GPPG. Anybody who plays with Bison style parsers, this is no news to you. The scanner is flex-like also, so nothing surprising, but there are some tricks. And it took me 10 days to get the language up and running and 4 more to get this convoluted demo. So it's not bad at all. So just go on that website, codeplex.com/ironpython, download the damn thing and play. And send us feedback to dlr@microsoft.com because we want to hear from you. And we want your languages to work, yes. Good question. How do I get the debugging support? For the most part, it works. What was difficult is each DLR node in the tree has a span that you associate with it. And these spans are used essentially from where to where in the file it goes. And these spans are used to generate the breakpoint locations as you step through the code. So in some cases, like, let's see, the whole program, I think I can find it. Program in the lol code. So here's a make function that the parser will call to make this node. It's the gen that will actually generate empty statement upon entry to it. So when it's the location of the height at the beginning. So just by virtue of putting empty statement in here, the debugger will stop on the height. And same for the things by at the end. So sometimes it took little tricks like that. If I do care about the location explicitly, then I need to play with the spans a little bit. It wasn't bad at all though. Mostly it was like I just didn't put the spans in the DLR tree at all, and then my debugger was lost. But then to fill them out was not a problem. Any more questions? Yeah. code DOM, and is there a relationship between DLR trees and code DOM? No. No relationship at all. As far as I know, the code DOM essentially you build, and there are experts around here that actually know about this stuff. I don't know about code DOM. But as I understand it, you build the tree in code DOM, and then it, for the most part, gets serialized into actual text, which then they throw to the compiler. We're all in memory. We're very much like link trees in that sense, link expression trees. There was a question in there somewhere? Yes? Yeah, we haven't done all languages. Essentially, our support was, or our intent was, so the way we started was we had IronPython. And then we said, well, maybe we can extend it to other languages like Python and grow from there, as opposed to coming up with the biggest possible runtime to run them all. We are taking the approach of adding languages and perhaps extending the runtime to what makes sense to be there. So right now we have IronPython fully running. We have Ruby, which is running very well. We have JScript. We are playing with other languages like lol code, but nobody can expect that to ship in Visual Studio, honestly. So yeah, but we're kind of growing them, and there are people even outside of Microsoft who are starting to use DLR. Still, it's alpha, so if you do use it, get in touch with us, and we'll help you out. We'll work with you. Yeah. Oh, Prolog, yeah. I mean, there are languages that the DLR just may not run, simply because of the design approaches we took. And we're hoping to run many. We're hoping to run many popular ones. If we're going to run all of them, probably not, but hopefully many. Yes. Those are more questions. Yeah. Yeah. Is it going to run on devices? If you were at the talk before this one, the answer would be simple no, because the compact framework is missing one feature, and that is lightweight code generation. So all this magic that's happening, where we ask a question and the language tells us a little bit of tree, we compile it, all that is generating code and runtime. The compact framework implementation does not support that. So IronPython as is does not and never did run on .NET Framework. We hope to one day fix it once the compact framework catches up, but no, for now, not. More questions? I saw one hand somewhere over there, but I forgot. No? Yes? Sure. Yeah. So thanks everybody for coming, and